here's another circuit that will oscillate for us, the RLC circuit. You can probably guess what that is. It's got an R, and it's got an L, and it's got a C. A resistor, an inductor, and a capacitor in series. So we use our little fiction here and think about the potential drop around each one and add them up and get 0. So around the capacitor we have a drop of Q over C, negative Q over C. And then, I drew them from a different order from my equations. And then the resistor is, of course, minus IR is the voltage drop across the resistor. And then the inductor is minus L di dt. Now let's say that's equal to 0. So, more complicated equation. What we want to do is, we want to switch to charge is usually the best thing. So we take our currents to dq dt. And you also, it's usually best when you're dealing with a differential equation to isolate your highest order derivative. So that was going to show up here. We have d2q dt2 there, right? Because I is dq dt, and then a derivative of a derivative is a second derivative. And we want to isolate it, so we want to multiply the whole thing by minus 1 over L. If you multiply that by minus 1 over L, then you'll get plus 1. You'll get just d2q dt2. So if we do that and reorder them a little bit, we get d2q dt2 on that term, plus, and then you would go to your next order derivative. Let's see, that's positive R over L, and then dq dt, and then also positive Q over LC. Where in this case, remember, Q is a function of time. We're trying to figure out how does the charge behave in this circuit. And you multiply the right side by minus 1 over L, and you get 0 on the right side as well. So with the LC circuit, we went through that whole process. We looked at it. We couldn't just solve it by integration. We had to think about it. We guessed a solution. That's what they really do. We guessed, and we plugged our guess in, and we did it in great detail. Now we're going to do it in less detail for this one. We could do the whole thing. And if you knew a lot about complex exponentials, we could do it all in detail. But for this one, just to get us moving along, we're going to guess. And guess is in parentheses here because I'm telling you the right answer because I have done this before. And my guess is Q of t equals A e to the minus bt times the cosine of C. Do I want to use C? Yes, the cosine of CT. So we made sort of a general guess with 3 parameters, where this is some, you can tell, some maximum charge. Right, because this, it's some maximum charge. And BT, this represents the damping. Right, so the circuit has a resistor in it, so maybe you can imagine what's going to happen. It's going to have oscillations, but they might damp. So the damping is in that exponential decaying term, and then the oscillations are going to show up here. So even if I didn't know this was the answer, this is a good constructed solution. Well, it's going to have some amplitude, it's going to be damped, and it's going to oscillate. Seems like a good guess. All right, so let's see what happens with that guess. So we're going to plug in the guess. And if we were to do that, we would find that it is good if these things are true. These are the equations that would fall out if you plugged the guess in. A would be equal to Q initial. The initial value of charge that we were to build up with some initial condition, A would be that value. B would be R over 2L, and that's basically the damping rate. So just like we thought in that part of the equation, B looked like the damping part. That's the value, R over 2L. And then C And here's something that happens in physics. There are two C's, right? So here, C is the capacitance of this circuit. But in the answer, C was one of the parameters we stuck in the answer. We only have so many letters. It happens. You have to get it out of context. Sometimes it's hard. I didn't mean to do something this bad, though. C is the square root of 1 over LC minus R over 2L squared. And that is the reduced frequency, or it has a lot of names. What that's telling you is you'll have some initial charge, the motion will be damped, and it will be an oscillation. This is the frequency of the oscillation. Remember, the square root of 1 over LC was the frequency of just a pure LC circuit. When you add resistance in, what it does is it oscillates at a lower frequency. It's the reduced frequency. Sometimes it's called omega D for damped frequency instead of omega naught for just the square root of 1 over LC. And here's that evil thing I did. This is the capacitance, and this is that parameter C. I put two C's in one equation. Normally I wouldn't do that to you. I'm trying to demonstrate what can happen in a lecture. So you got to be ready. You got to be ready to get it from context. If you see a C right next to an L, you know that means the capacitance. If I'm laying out the values in this equation of the previous guess, A, B, C, you know that's the C in the guess. Sometimes it happens, you got to go with the flow. Okay, so if we put all that together, it would look something like this. I don't want to mess this up. Q as a function of time would be Q max, or Q init is what I called it. You could call it Q max as well because it's the highest charge you'll get. E to the minus R over 2LT cosine the square root of 1 over LC minus R over 2L squared T. So that's your full mathematical solution. So we made a guess that looked a lot like that. Now we've plugged it in and solved for the three parameters. So now let's plot it. Let's look and see what would it really look like. Let's see. Now this would be Q as a function of time, and we have a time axis like that. And it's going to start at some Q initial, or you might call it Q max, and it's going to oscillate and decay. So it's going to do something like this, like that. So you can see the oscillation very clearly. That's the cosine. And if you were to think about an envelope going around the amplitude of this oscillation, the envelope is like an exponential decay. So we could say this is the decay, this is the oscillation, and they happen together in an RLC circuit. Let's see, I could demonstrate this for you, but I already did. If you think back to when we demonstrated the LC circuit, the answer we derived was an oscillation, a sinusoid that sort of just went on forever. But if you look closely at the actual behavior that I showed you on the screen, you could see that it was going down. And that's because the real LC circuit I demonstrated had resistance in it. The wires have resistance. It's low, but it's not zero. And the inductor has a huge number of turns inside that inductor. That's a lot of wire, a lot of really thin wire, and therefore a reasonable amount of resistance that's hard to get rid of. So anytime you demo an LC circuit, you usually, well, you're always demoing really an RLC circuit. So you always have some level of damping in the circuit. The RLC circuit has different damping regimes. Its behavior depends on how much damping there is. So one is called light damping, or under damping is another name for it. It occurs when R is much less than 2L. From the solution, which I'll write again, Q equals Q initial e to the minus R over 2L T cosine, oh my gosh, the square root of 1 over LC minus R over 2 L squared T. Okay. So from this, you can see that the quantity R over 2L is pretty important, right? It's what's telling you how much damping there is here, how much the omega is reduced here. So in underdamping, R is much smaller than 2L. If that's the case, this is a very small number. This is like 0. This is a very small number. So basically, this is approximately e to the 0, which is 1. So it doesn't damp. And here, again, R over 2L is a small number. If you square it, it's a really small number. So this is approximately 0. And in that case, the circuit would oscillate at the undamped frequency, the square root of 1 over LC. It would oscillate as though the resistor weren't even there, if it were just an inductor and a capacitor. So if you wanted to plot this, I won't plot it in detail, but you can see what it would do is it would just oscillate. Cosine forever. The damping is essentially gone. So when we usually think of an oscillating RLC circuit, this is what we're thinking about, a really small amount of resistance that we can maybe even ignore. There's also, other end of the spectrum, there is overdamp. So overdamped is a special thing that happens as soon as R becomes greater than the square root of 4L over C. Okay? And by these C's, we mean the capacitance. There's no more parameter C. And you can see what would happen. Let's see, if you were to plug that in, if R was going to go here, we'd have Q, that's fine, would be Q init, that's fine. E to the minus, let's see, if this were the square root of 4 over LC, well, I didn't mean to do this. Let's see, R, this would be over 2L, the square root of 4L over C, and then divide that by a 2L, which would come in as a 4L squared. And then, I don't know, it'd be 1 over LC times time. So it'd still be damped by some amount. But then let's look at this cosine term. The square root of 1 over LC minus, and then if we made R squared here, this would be R squared over 4L squared. Well, if R squared is 4L over C, and then over 4L squared, that becomes, cancel, 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 cancel. It becomes minus 1 over LC. It's 1 over LC minus 1 over LC. Basically, it becomes so damped, the frequency is driven to 0, and it doesn't oscillate anymore. If R is greater than this number, this term becomes negative. This gets even bigger. You have the square root of a negative number. Then the frequency is imaginary, and it doesn't oscillate anymore. So in the case of overdamping, it doesn't oscillate at all. It actually does something like this. It starts up here, and it goes, and it actually never reaches 0, or it never crosses over. Just goes off forever towards infinity, and it never crosses over. If it's undamped enough, if the damping is low enough to cross over, then it's technically going to oscillate. But at this value and above, it basically never gets there. And really, to get the accurate solution, you shouldn't have made this guess. You have to make a different guess to the equation to get the right answer when you are overdamped. So there can be many behaviors depending on the relative values. There's not only one answer to the differential equation that describes the charge motion. It depends on the parameters.